Hey everyone, and welcome. Today we're going to tackle a real classic problem from Irodov's legendary physics textbook. It's one of those puzzles that really digs into what happens when one particle smacks into another. So let's dive right in.
So, at its heart, this problem isn't really about just plugging numbers into formulas. It's about a really fundamental question in physics. When one object hits another, how do they actually share their momentum and their energy? We're going to unpack this by looking at two very different kinds of impacts. So here's the setup. We've got a moving particle, let's call it M1, and it's on a collision course with a particle that's just sitting there, M2. Now the key phrase here is perfectly elastic. We'll see exactly what that means in a moment. Our goal, our whole mission, is to figure out the fraction of the initial kinetic energy that the first particle loses. Okay, before we can solve anything, we need to open up our physics toolbox. For a problem like this, there are two fundamental laws, two golden rules that are going to be our guide for this entire interaction. First up is the conservation of momentum. It's a big one. It basically says that the total momentum of our two-particle system before the collision has to be exactly equal to the total momentum after. And the crucial part here, the thing you can't forget, is that momentum is a vector. It has both a size and a direction. This isn't just about speed, it's about which way things are going. And our second golden rule is the conservation of kinetic energy. Now, this one has a catch. It only applies because our problem specifically says it's a perfectly elastic collision. What that means is no energy gets wasted. It's not lost as heat or sound or anything like that. The total energy of motion before the crash is identical to the total energy of motion after. And this slide really nails the difference. For an elastic collision, you should be thinking of two billiard balls just clicking off each other perfectly. For an inelastic collision, imagine throwing two lumps of clay at each other. They stick together. Our problem is that ideal, clean billiard ball scenario, and that's exactly why we can use both of our golden rules. Right, let's get down to it. We're going to tackle the first scenario from the problem, and this is the more complex case. It's a glancing blow, where our incoming particle M1 gets deflected by exactly 90 degrees from the direction it was originally going. Here's our game plan. This is how we're going to attack it. First, we'll draw a picture of the momentum vectors, super important. Then, we'll write down our two conservation laws as equations. And finally, we'll just combine them with a little bit of algebra to find the answer. Honestly, having a clear plan like this is key to not getting lost in the math. Okay, step one, let's visualize this. The initial momentum, which we'll call P0, belongs entirely to that first particle. After the collision, that momentum gets split between P1 and P2. Now, because momentum is conserved, the vector sum of P1 and P2 has to equal P0. And since the problem tells us P1 flies off at a right angle, bam! These three vectors form a perfect right-angled triangle. Understanding this picture is the absolute key to the whole solution. And this geometric picture immediately gives us our first equation. I mean, as soon as you see a right-angled triangle, you know what to do, right? The good old Pythagorean theorem. The square of the hypotenuse, in this case p squared, is equal to the sum of the squares of the other two sides. This is our conservation of momentum law, just expressed with geometry. Pretty cool. All right, that's one equation down. Now let's move on to our second law and see how this all connects. We just write down the conservation of kinetic energy. The initial kinetic energy, T0, equals the sum of the final kinetic energies, T1 plus T2. And by using that handy formula that kinetic energy equals p squared over 2m, we can write this entire equation using momentum, just like our first one. Now, both equations are speaking the same language. So here's where the magic happens. We now have two independent equations that came from our two golden rules. The rest is really just algebra. It's like a little puzzle. We can substitute one equation into the other to get rid of the variables we don't care about, like the final momentum of the second particle, until we find the one thing we're actually looking for. And after all that, we get this, a surprisingly simple and really elegant result. The fraction of kinetic energy lost by the first particle is just the ratio of the masses, m2 divided by m1. That's it. So think about it. If the masses are equal, m1 loses all of its kinetic energy in this very specific 90-degree collision. Fantastic. Now let's tackle the second case from the problem. And you'll probably be happy to hear this one is often much more intuitive for people, the direct head-on collision. All the motion is just happening along a single straight line. You know, the great thing about a one-dimensional collision is not all that tricky vector stuff just goes away. We don't need to worry about triangles or components. Direction is just positive or negative. We still apply our two golden rules, conservation of momentum and kinetic energy, but the equations we get are just a whole lot simpler to solve. So, after you work through the algebra for this 1D case, this is the general formula that pops out. The fraction of energy lost depends on the masses in a little bit of a more complex way, but this formula is incredibly powerful. Why? Because it lets us predict the outcome for any combination of masses in a head-on elastic collision. And now for the fun part. Let's really test this formula and see if it makes sense in the real world. So, what if two equal masses collide, like billiard balls? The formula says the first ball loses 100% of its energy. And that's exactly what happens. The first ball stops dead. Okay, what if a tiny mass hits a huge one, like a fly hitting a wall? The formula says it loses basically zero energy. It just bounces off. And what if a huge mass hits a tiny one, like a truck hitting that fly? Again, it barely loses any energy, it just plows right through. The formula totally matches our intuition. So after solving for both of these cases, let's just step back from the equations for a second and look at the big picture. What are the really important takeaways from all this? Well, first, direction is everything for momentum, but it means nothing for energy. That whole vector versus scalar distinction, it is absolutely fundamental. Second, the geometry of the impact, whether it's head-on or a glancing blow, completely changes how the energy gets transferred. And finally, getting a general formula, like we did for the head-on case, is just so powerful because it lets us understand the whole range of possibilities at once. And hey, don't just take my word for it. The author of the problem himself, i.e. Irodov, said this in his book. Solving in the general form with all the variables isn't just about getting an answer. It's about understanding the deep physical relationships that are really at play. So we've explored this clean, ideal world of perfectly elastic collisions. But it kind of leaves us with a really interesting question, doesn't it? What happens in most real-world collisions where energy is lost and things get messy and might even stick together? Well, that's the world of inelastic collisions, and that is a fantastic topic for another time.